Good afternoon. I'm Sidney Porter. I'm here on behalf of the Health Physics Society History Committee to videotape the long and productive professional career of Dr. Joseph Soldat. Joe has been working since 1949, I believe.
48.
Or 48, 49 in the health physics field. He is one of our true pioneers. And it's my pleasure to introduce to the videotape Joe and to ask Joe to tell us about his early years and the things that he's done concerning health physicists, health physics, and the people and the health physicists and professionals that have shaped his career. So Joe, why don't you tell us about your very early beginnings?
Well, I came to Hanford in 1948 with a degree, bachelor's degree in chemical engineering. And they were hiring chemical engineers and physicists to train them to be radiation, I guess you call them radiation engineers in those days. And we were trained, we were sent to school to study all about radiation, its effects on matter and on people, and counting and decay curves and all kinds of strange things like feathers analysis. And so on. And some of the instructors we had were, Jack Healy was included. And he was a very knowledgeable, all-trained mathematician, who I think was his field. But he knew the radiation work quite well.
Did Herb Parker teach any classes?
Pardon?
Did Herb Parker teach any classes?
I don't remember him teaching a class. Herb was in charge of all of the radiation protection, and he had great authority for safety matters at Hanford. Over the years, the production people had tried to exceed the limits that he had set because they have a special push and need more plutonium instantaneously or something like in the early 60s. But I have letters in my file, and Herb Parker wrote to production people, says, no. You can't do it. I've set my limits based on average conditions, and I don't want them to be exceeded because you might have unusual meteorological conditions during that period to greatly exceed the limits I've set. And he made it stick. W.E. Johnson was in charge of the whole project, and Herb reported directly to him and had great authority over the safety. Herb was kind of an interesting guy. He was trained in England, and your first impression was he was kind of stuffy. But when you got to know him, you found out he had a dry sense of humor. And he could kid once in a great while. His other characteristics I remember, he was a great wordsmith. He always knew the correct word to use in a sentence or in a situation. It always had the exact meaning that he wanted. He also was very critical of written documents. If you gave him something to review and he found one error in English or grammar, he would go over that paper with a fine-tooth comb and really mark it up. and you know, I didn't have him reviewing very many of my papers, fortunately, because I was way down the bottom of the totem pole. But I experienced some of that.
Who was your direct supervisor in the early days?
Originally, when I got there, I had to wait 5 months for my Q clearance. I worked in bioassay, and a fellow by the name of Jim Sainline was my supervisor. And I was doing statistical analysis on bioassay results, but I was not allowed to know what it was I was analyzing because I didn't have my clearance. But then when I got my clearance, I went out to T-Plant, fuels reprocessing plant in 2 East area. And I worked for a fellow named Frank Tabb, who was in charge of that 200 area operational safety. He reported to Art Keene, as I recall, who was in charge of all of the 200 areas combined. And he was Frank's boss. Art stayed around for quite a few years. Later on became head of the radiation protection operation in Hanford Labs when that was put up as a separate entity. He was a very good manager, except he if he got suspicious of someone and didn't quite like what they were doing, he was on them all the time, leaning on them, you know, and asking them to write, don't say it, write it, on what they were doing and whatnot. But one time, I was really impressed. He rotated his people around to different aspects in health physics. You may be supervisor of operational monitoring one day, and pretty soon you're in charge of bioassay, or whole body counting, or environmental monitoring. And he moved people around and tried to train them in the entire field of health physics. And I thought that was great. One day he told me he was leaving town. He wanted me to fill in for him. He was going to be gone for 2 weeks. And he said, when I come back, I don't want to find a lot of undone work. If you have to make a decision while I'm gone, make a decision. Even if it turns out to be wrong, I'll be less mad at you than if you let the stuff pile up for me to take care of when I got back. That really impressed me. I thought Art was really a neat guy. One of my first assignments, like I said, I was in T-plant, and I had a habit of getting cuts, and I wouldn't notice it. I'd cut my finger, and I wouldn't realize it. And they decided I was not fit to work in the radiation zones because you can't go in when you got an open wound. So they put me in environmental monitoring. It was the best thing that ever happened to me. I really enjoyed my work in there. I did a lot of things. A lot of calibration work.
What was your first assignment that you remember?
One of my first assignments was to calibrate the counting equipment. We had a glass-walled GM tube shown here in blue, surrounded by a brass cover with a slot in it, and there was a pump that drew air in around the tube and out, and the tube was connected to counting equipment, and there was a filter paper, CWS 6, Chemical Warfare Service, number 6 filter paper. And they wanted to know what kind of counting efficiency they had using that setup. So I got the lab to make up some sources of different radionuclides and put them on the filter paper, sort of evenly, and then I put them on the tube that I had in the lab and counted. And then I plotted a graph of counting efficiency, counts per minute per unit amount of radioactivity versus the beta energy. And I got almost a straight line. It turned out that principal interest at that time was I-131, and efficiency was only about 3% for that, on that one.
Now, Joe, let me ask you something there. Wouldn't you have some iodine that would go through the filter paper and play it out on the tube?
I don't know. It probably could have. Yeah, because not all the iodine was particulate.
That's my point.
Very small amount of it was particulate, actually. But iodine also probably would be eluted off as the air flowed through. It wouldn't build up for a very long time because it's 8-day half-life. You know, if you want, it changed the filter once a week and took it into the lab and counted it. That was just a kind of a real-time indication of what might be going on.
Which is important, very important.
Which is very important.
Especially on an emergency basis.
Oh, yeah, right, right. The other thing I did, I had the lab make up some sources on white pieces of filtered paper. Take some readings so that I could translate that into readings you might get from contaminated ground with several different isotopes. And using a CP, a cutie pie, barrel instrument with a pistol grip.
Well.
And
with a styrofoam cup on it.
Well, it had a plastic Bakelite cover that you could put on, take off. And the window open, window closed, the GM, window open, window closed. I took all those readings on the different isotopes. And then I assembled the data. I noticed that a lot of the nuclides had similar readings. And I put together a package on paper of nuclides that might represent 100-day-old fission products released from the stack, because at that point in time they were using a 100-day cooling period for the fuel before they dissolved it. And if we had a release of that kind of material and go out and survey the ground, you get an idea of how many microcuries per square meter might be on the ground. That and some other things like that I did ended up in IAEA's Emergency Monitoring Manual, or report number 19.
That was a very useful manual, and the first one that I was aware of that came out that was so comprehensive.
Yeah. Art Keene was asked to go to Vienna and work in a committee that put that stuff together, and I helped him gather up all the Hanford stuff. It turned out that the Hanford words, which were mostly mine, were about 25% of that manual.
Very impressive.
It was I actually went through and counted, because I saw a lot of our stuff got in there. It wasn't all my words, but it was stuff that I put in.
Would you like to tell our viewers about the old Hanford GM tube under the armpit measurement that was in that manual? That's the one that impressed me so.
If I know what you're talking about, I think it was for sodium.
24, yes.
Sodium 24. If you were exposed to neutrons in an emergency, the neutrons would activate the sodium in your blood. Of course, there's a lot of sodium in your blood, and sodium gives a very high gamma, and it has about 15-hour half-life. And you could stick a GM under the armpit and get essentially surrounded. GM would be surrounded by tissue that way, and you could get a reading and kind of get a quick and dirty estimate of how much neutron exposure a person had, or whether they'd been exposed at all.
Which was a very important...
That was developed not by me, but by some of the other people in our radiological engineering group.
I just thought of it, when I first saw it, I remember thinking, how clever. Really, because it's so quick, so dirty, and it helps you triage right after an emergency.
There was another clever thing that you remind me of, and that was for P32 measurements in people. P32 was a problem in the Columbia River for a while. And at the peak year, about 1963, the amount of P32 in whitefish collected in the Columbia River, if you ate like a half a pound a day every day, was approaching the then limit of 1,500 millirem per year to the GI tract. And to solve this problem, Dr. Earl Palmer developed a very thin beta phosphor that would record counts from P32. And he realized that your blood is very close to your skin in your cheeks. That's why you get red when you blush, because your blood is right here just below the surface. So he decided that he could put this counter up against your cheeks and measure P32 in the blood. And one of the things some of us did was ate some whitefish or drank some P32 solution and then laid down between some restraints to keep our head from moving so that he could try out his counter. It sort of worked. It never got to be fully developed into an operational instrument, but it did work. He was always experimenting. He worked at the whole body counter. And he wanted to calibrate something for zinc 65. He'd drink a little solution of zinc 65 and then jump into the counter. Herb Parker didn't appreciate these kinds of things.
I remember that Herb telling me that there was a big surprise on the amount of P32 found in the Columbia River early on. You want to
well, I don't
that?
remember about the surprise, but about 1959, they upgraded the power level on the reactors. At P32 would increase in the effluent water in the spring when a certain amount of debris, dissolved or suspended solids would come down the river. Of course, the water was treated, but the dissolved material stayed in there, would go through the reactor and activate the precursors. And one of the things, I think arsenic was used in the tubes for seal when they were welding the end caps on the tube. They had arsenic in there, and there were other things in the water. And the P32 concentrations in the effluent were higher than you would expect from the flow time through the reactor and back out. And they finally decided that there was a film forming on the fuel elements. and holding up the precursor, the P-32, so it could get additional radiation. And we had a fellow named Wyatt Selker in the lab in the building that I was in, and he was studying all kinds of ways to take P-32 out of the effluent water. He tried aluminum turnings and all kinds of flammable solvents, and about once a week he'd have a fire in his lab, and we'd hear the fire siren. We'd say, "Oh, Wyatt's at it again." And I don't think he ever did really find something that would remove it completely. I think they ended up having to treat the water differently going in to cut out the precursors that were forming the P-32. It finally was taken care of and reduced to a more tolerable level. But our principal interest in the environment about that time was whitefish, which is a species of trout in the Columbia River. I think they taste terrible. I don't know why anybody want to catch them unless you smoke them. But they would accumulate P-32, and it was temperature dependent. The accumulation was almost like a fifth power of the water temperature or something. And in order to understand the uptake of P-32, a fish biologist by the name of Dick Foster decided he would be willing to eat whitefish once a week caught from the Columbia River. And they measured the P-32, he fried the fish, and he ate it, and they measured the residue in the frying pan, and they figured out how much he had taken in, and he went down and he was counted actually for zinc-65, which you could count in the whole body counter, which was related to the P-32 in the whitefish. And the biological half-life of the material in his body matched pretty well what ICRP had in their handbooks, except one time when we had the criticality in the fuels reprocessing plant, the Recuplex incident in 1962, I think it was, April 7th. And he managed the swing shift level of the emergency crew. And we worked down in the basement of the federal building. During that period, the half-life of the zinc decreased. It was removed faster from his body. Now, I found an article in Chemical Engineering News magazine that talked about zinc in rats and how they excreted more when they were under stress. He didn't appreciate me showing that to him. He said, "I'm not a rat." But that actually happens. Under stress, your digestion is different.
Now, did you publish? Did someone publish on this?
All the stuff about Foster's ingestion was published in the Health Physics Journal. Several articles on zinc-65 and P-32, at least 3, over in the 60s. The other thing that we published for our work was in the big iodine symposium publication. Volume 9, number 12, Health Physics Journal, 1963. They had the iodine symposium in Hanford. Leo Bustad was in charge of that.
Remember Leo, yes.
And I had some papers in there. I had a paper in there on the 40 curies of iodine released from Purex in our sampling and results for that. There were some papers on the uptake and retention of iodine by cows when they were fed stable iodine and what got in the milk. Some of us actually drank the milk with the iodine in it to see how it behaved in their body, and behaved sort of like what the manual says it ought to, you know. And I sat down one day and calculated what my dose was from the decay curve, you know, in my thyroid. I think I must have got about 10 millirem from the experiment, which is about all I got. One other time we had an experiment where 2 of us stood out in the field and inhaled iodine that was being released by the Met Tower, and they had samplers all around. We had things on our chest to measure our breathing rate, and a gas meter, the total gas that you inhaled. Wow. And we had thyroid measurements after that. And the uptake and decay again was even closer to the standards in the manual than the milk drinking was. But Herb Parker found out about that. He was mad that he wasn't properly informed. He said, those people should have had thyroid checks before they went out there to see if they were normal. And you know, we had all this paperwork which he should have filled out. He didn't appreciate some of these things that were done without his knowledge. You know, he would like to watch over everything and make sure it was safe.
Now, Joe, you had a lot to do with planning the overall environmental monitoring programs.
Well, a little bit. I wouldn't say a lot. You know, when I moved into the program, it was already underway.
But that was what, 48? 1948?
I moved in 49.
49.
And things did change a lot over the years. Not always at my instigation, but we were sampling a lot of sagebrush at first, all over the project and off-site. Then we decided that we should expand the program, and we took samples all the way up to Spokane and back. This was after the green run that they decided to do that. So they routinely went up to Spokane and sampled
What do you mean the
vegetation.
green run?
Okay, the green run was an experiment that the military conducted in November 1949 at Hanford, where they deliberately dissolved very short cooled fuel, which had a lot of noble gas, a lot of short-lived iodines, things in it. And one of my jobs for that experiment was to calibrate handheld instruments that you could hold up in the cloud and read the iodine concentration and get an estimate of how much was going by. And there's just crowds of people out there in the cloud, managers, radiation monitors, and engineers like myself. Of course, nobody had any salt masks on, no respiratory protection. We're walking around in this iodine.
Was everybody?
We knew it wasn't a problem. You know.
Was everybody whole body counted afterwards to show it was not a problem?
We did not have a whole body counter in those days.
Okay, well, what year are you talking about here?
1949.
1949. Okay.
They took a lot of vegetation all over. In fact, on the project, they had a grid which was a half-mile space laid over the project. We sampled vegetation in every one of those places, and then they sampled off-site all the way to Walla Walla and up north and all around. And of course, everything was secret. We didn't know why they were doing this. And a secret report was written with the help of Jack Healy and the military. And later on, there was a lot of public concern when this was revealed that this had been done, you know, without public's knowledge, and they felt kind of like they were guinea pigs, which really wasn't true. The guinea pigs were the vegetation we were trying to, and the air monitoring. They were flying around with planes trying to figure out what they could measure from a reprocessing plant. And I don't think to this day they have really released the basic reasons for the experiment.
I remember that some of the meteorological data or lessons learned from the release of the iodine were talked about in meteorology and atomic energy.
Right.
And I'm not sure that they said where they got the data from, but the point is it gave extremely good data that Gifford said was absolutely essential to understand meteorology.
Yeah. Well,
and everyone always wondered where that data came from, and now you're telling me.
The year that I stood out and inhaled iodine, they had several iodine release experiments with a lot of data collection, a lot of towers and sampling at different heights in the towers, and a lot of them spaced out in semicircles around and downwind from the towers. So a lot of that data may have come from that. They also released a lot of particles, alpha particles, and they measured these on the filters with zinc sulfide. And all of it was zinc sulfide particles they released, and then they measured them by activating one way or the other. I can't remember exactly, but there was a lot of data on dispersion, and they developed a lot of meteorological models for the Hanford terrain,
right,
which is not typical of a lot of places in the country. One was called the green glow experiment that they did. And I guess the zinc sulfide, that's what it was. The zinc sulfide would fluoresce when you expose it to the right wavelength of light, and then they could count stuff that way.
By the way, you know, in the Nobel laureate write-up on Pierre Curie, he's the one that discovered the fact that if he used the radium rays, that zinc sulfide would fluoresce. And part of his Nobel laureate prize was for that discovery of fluorescence.
Well, that's where they got the idea probably for using the zinc sulfide. And it was essentially innocuous material that you could release. The other thing, after they had a problem with the ruthenium release from the redox fuels reprocessing plant. The ruthenium was not efficiently removed by the hexone solvent during the process. And they had a separate step to remove ruthenium downstream from the normal fission product cleanup. And it involved oxidizing the ruthenium to the right valence level so that it could be precipitated in I believe it was caustic scrubber. They oxidized it with potassium permanganate. And the scrubber failed one time. And they put out about 350 curies of ruthenium out the stack. And it was kind of like white flakes because ammonium nitrate, which is formed during dissolution of the fuel elements, occluded the ruthenium into white flakes, and it's almost like it was snowing on the ground in the vicinity of the plant. Some did get off-site, but most of it was local. It was like snow. It was widely dispersed, of course. It didn't cover the ground, make it white. But this happened in New Year's weekend, 1954. And I've learned after that a lot of accidents happened on holidays.
Yes.
And other people have told me, well, during shifts or during weekends, somehow people's attention may be a little less than it should be. But what I was doing, my principal job was to monitor the laborers, the truck drivers, who went into the areas that were contaminated and posted keep out signs. They cleaned up the roads pretty much, hosed them down to clean up the ruthenium and wash it into the edges of the road at least. And we also, at that time, developed our first vehicle-mounted road monitor, so we could drive down the road and monitor for
Were you using sodium iodide? What were the detectors?
They were sodium iodide. And ruthenium has a distinctive gamma peak. There's two rutheniums, 103 and 106. The ratio depends on the age of the fuel.
Yes.
And each one has a distinctive gamma. But I think we were mainly monitoring just for gamma contamination. Any contamination was not wanted, so if you found it, well, they'd clean it off the road. The other thing we did is we set up little plots of 1 square meter and numerous plots all over the project, a couple off-site, that we revisited frequently, like once a week at first, to measure the particles and see if they were moving or how fast they were disappearing. And one of the interesting things was that the particles of ruthenium disappeared twice as fast as the decay alone indicated. A lot of loose sand. I just kind of assumed the sand was blowing around to cover them up. And if you plotted a decay curve, you could see ruthenium 106 and ruthenium 103 components. Each one appeared to have a half-life, exactly half of what the normal radiological half-life was. And one of the things that was calculated, and I think Herb Parker had a hand in that, and that was if someone was sunbathing, laying out in their lawn on one of these ruthenium particles, what would happen, you know? And so the biology folks got some pigs, and pig skin is about like human skin.
Yes.
And they're the only other animal that can blush, I've been told, besides man. And so they got lots of the ruthenium particles that we collected, and they put them on pig skin to measure the burns or ulceration that might happen, and got a bunch of data on how they behaved. One of the problems with that release was they were building the Purex reprocessing plant.
Yeah.
The contractor had a no radiation zone work contract. And the whole area where they were working was peppered with hot ruthenium particles. So 4th of July weekend, 3 or 4 day weekend, radiation monitors and supervisors and everybody was given a GM, and we walked side by side over the whole area. If we found a hot particle, we'd stop hold the GM on it until the laborer with a bucket of sand caught up, scoop up the particle, put it in the sand, and then we could move on. And they picked up that whole area and cleaned it up totally, as we could find, in one long weekend. Of course, the monitors made lots of money, 16-hour days and double overtime on Sunday and all that. Of course, I didn't. I wasn't on overtime.
Now, what were you using? What kind of detectors?
It was the just 1B85 GM, the walking stick. The small ones are about the rectangular box dial on the top front. In the early days, we had those crazy Victorine GMs. They worked well, but they were the size of a briefcase, weighed a lot. You didn't have to carry that everything when you did your ground surveys. The other old instrument we had was it the Victorine, heavy thing about like that with the round front and a dial that rotated. The sample people that went into the Hot Canyon building to take samples, dip tubes out of the tanks, would carry those and set them down, and they had these big heavy, they call them doorstops. They put the sample in and they would take a reading with this instrument. And they were called doorstops, and the sampling tubes they used were called trombones, because they put the tube down and I guess they withdrew the part of it and it sucked up the liquid sample. And then they would take them into the lab.
Tell me some more about the metabolic data of environmental radionuclides through the environment that you were working on.
Oh, well, I like to think that I developed the first real comprehensive food model, which for something called the year 2000 study that AEC wanted done, or ERDA. It became ERDA before the project was done, I think. What we wanted to do...
What year did you do this?
Well, it was 68, 69. Then what happened is they wanted to know, reactor development people in AEC wanted to know if we had a full-blown nuclear economy in the United States with lots of reactors, lots of reprocessing plants, what the dose would be to the population. We decided, excuse me, we decided to settle in on the Midwest because Battelle had done a lot of work in the Midwestern region, and there were a lot of power plants already there, and they had studied the water and the river basins and all that for other projects. So we picked that part of the country to start on. And what they did was dose equations for submersion and inhalation and ingestion, which I modeled after what was in ICRP publication 2. And then we decided we needed to know doses from food. And so we put together a model. I wrote out a model that says you'll have deposition on the leaves, you'll have deposition on the soil and root uptake, you'll have water that's contaminated you might irrigate the plants with, both directly to the leaves and also on the ground, and more root uptake. And then you had animals that would eat the plants. And very little known about animal biological behavior. There's only a few nuclides that have been studied, like strontium-90 in milk cows, and cesium for fallout. And then people drinking the milk and eating the meat, and eating vegetables, leafy vegetables and root vegetables and all that stuff. And the fellow who, believe it or not, was a forest hydrologist, had been working in Canada in a forest. He came to treeless desert at Hanford, and in order to give him something to do, he helped me. He went up to WSU, Washington State University at Pullman, and looked up all the agricultural data for animals, how cows were fed, how much hay, how much water, what the seasonal change was. He brought all that stuff down. And I looked in a lot of publications for data on uptake in plants. One of the best was Yook Eng's, remember Yook, Y-O-O-K-N-G, from University of California? I think it was at Livermore. He did a lot of stuff for the fallout people. And he had publications of element concentrations in soil versus element concentrations in plants. And a lot of that data was very helpful to go into my model. Other things I found when we got into aquatic life, the Russians had done a lot of work on the uptake of radionuclides in fish and aquatic biota, and that data was useful. But there were big holes. You know, there's a lot of nuclides that were not covered by the data, and we wanted to do, we had about 72 nuclides. We were trying to get the principal ones from reprocessing mostly. And so the fellow and I sat down and we looked at the chemical table and looked at elements that we didn't have data for and said, well, this one probably would behave kind of like this. And we did that, picked out numbers, and the guy was clever. He said, well, you know what we ought to do for the nuclides we're not sure of, for plant uptake, we'll put a number in the calculation that's exactly 9.9 times 10 to the minus fourth. All the other numbers were one significant figure, and anybody that looks at that will know that number is fuzzy. And if they got a better number, they can use it. So we did that. And that worked out, I thought, real well.
Did the publication explain that?
Yes. We had, we published this for an EPA symposium on environmental radiation. It got published in the proceedings of that meeting. The model was called FOOD, F-O-O-D, Fallout on Diet. That's what it stood for. And we had lots of fun with that. And I used that model for the BioMoves project. They had a project after Chernobyl called BioMoves, in which all the countries, several countries, were asked to use their environmental models to predict, if we give you the air concentration, predict what would be in the vegetation, what would be in the milk. And I made a one-page worksheet. I had my pocket calculator. I put in the necessary parameters, the air concentrations, and I went through and I modeled all the way through to the milk concentration, just from that one-page sheet. And all these other guys had 4-hour computer programs. You know, we had a meeting in this country and talked about the results. And they said, "Oh, we've made some mistakes in some of the data. We're going to correct the data, the input data we gave you." So that night, I went back to the hotel room, recalculated all my stuff, and had the answers the next morning. And those guys said, "Well, we got to get back to the lab and put this through the computer and everything." Owen Hoffman from Oak Ridge was one of the major domos in that program. And after it was all over, he exaggerated a little bit. He said, "Oh, Joe, he did better on the back of the envelope." A lot of these guys did. But that was the result of compensating errors. That's part of Soldat's law of compensating errors. What happened was I had not put down the correct deposition velocity for I-131 during rain. Somebody had told me that deposition velocity wet is the same as dry. Well, I should have added the two together. Instead of saying it's 1 centimeter per second, I should have said it's 2. So I would have come up with higher vegetation, but I would have overestimated the milk if I had. Turns out that for Chernobyl, the milk, the grass ratio was different. It was 1/4 of what we've been using for years.
Why is that?
I haven't the foggiest idea. My guess is that it was the nature of the material. High temperature, maybe some of it was ceramic, I don't know. But instead of 1%, it was 0.24% transfer from feed to milk. So, but that's why my law of compensating errors worked out, and I got pretty close to the right answer for that one. That's happened to me quite a bit. One time they had a release of iodine from a test reactor, and I had an experimental charcoal tube on there, and I waved a GM over it. Let's see. Oh, I don't have to worry about the environment. Well, milk won't be over 20 picocuries per liter. Well, it turned out the milk was 18. But
wow.
It didn't go straight across the river at the farm over there. It turned, the wind turned, and it went upstream to a farm several miles away. That's where the peak was. And the other thing with the problem, I forgot about the I-132, 135, 134, all the short half iodines in that charcoal tube. So my interpretation of the reading was off too, but compensated. I got the right answer.
Yeah, because in the early hours of an accident, of course, you have a lot of 133 anyway.
Yeah.
And at TMI, we saw 133 for about 2 days after the accident.
That's right. The I-131 is only about 10% initially of the total mixture of iodines. Yeah, I'd forgotten that. But that was about 1965. Another interesting thing that happened is Purex reprocessing plant, 1963, again, holiday, around Labor Day. They mistakenly got some short-cooled fuel to dissolve. It had gone through 3 individual checks of the age of the fuel. When the guy at the reactor area said, I want 118-day-old fuel, he says, okay. He went and got some fuel, but it was the wrong fuel. It was short-lived. He signed off on the ticket. The guy who double-checked him signed off on the ticket. And when it was shipped, the guy who received it signed off on the ticket. And at that time, they did not have a high radiation level alarm in the canyon building, the building where all the cells were for reprocessing. And so what happened is they started to dissolve the fuel. My stack monitor alarm went off. Boy, you guys have put on a bunch of iodine. So we went out and got a bunch of vegetation samples. No iodine. No iodine, no, just normal amounts. And what's going on? Well, it turns out what the alarm was measuring was noble gases. And the iodine, because they were using mercury to complex the solution in the dissolver, was staying in solution until they transferred the solution. After they shut everything down, they later transferred the solution to a holding tank. When they made the transfer, the iodine come out. So we went back to the same locations we had sampled previously and got more vegetation, so we had before and after samples for the vegetation. That was fantastic. But at least we knew our system worked and the alarms worked. And they rang in the what was called the dispatcher's office, where he controlled everything, and so he could tell something was going on from that.
Now, Joe, for years I knew all about the canyon building, and I was told that I could never discuss it.
Really?
Yes, it was. People were not supposed to know that the canyon building existed, that didn't have clearances. And so maybe what you could do is explain what the canyon building was, what it was used for.
Well, if you looked at it from the outside, it was a huge block of concrete, several stories high, plus probably another couple stories underground, with an attached smaller building that was offices.
It was a long building, as I remember.
It was long and skinny, very, very long. And inside was an instrument gallery where the instrument readings were on all the panels for the operations. Behind that was a pipe gallery, which was supposed to be clean, but contained pipes that had radioactive material in. And then there was the operating areas itself inside the canyon, where the vessels, the machinery, were down under huge concrete blocks, which step design, so they would nest down in, and those covers kept the radiation from coming out. And it was still a high reading if you wanted to go into the canyon surface and take samples like I was telling you about before, but at least most of the radiation was shielded. In 1949, when I was in T-plant, reprocessing plant, somebody said, we're going to try and do contact maintenance on one of those vessels down there in the cell that they used. So they put paper on the deck. We called it diaper paper because it was very absorbent paper. They diaper papered the deck. They went in with the crane and remotely pulled out the vessel, set it on the deck. And then I was supposed to go in and take a reading to see how long a guy could go in there. Well, they had a lever entrance to shield the radiation. I went and poked the instrument around the corner and went off scale, and I left. And I said, no way. They finally decided it was impossible to do contact maintenance. They had to do remote maintenance on the any of the things that they had to repair.
I remember in the middle 60s, I think it was also referred to as no man's land in there. In other words, they didn't want people in there at all.
Yeah, well, they had a crane cab up above where the crane operator would operate, and he was shielded. He also had to wear an assault mask in case there was an iodine leak or something. And he had an air filter on the cab where the ventilation air was. And he had a periscope so he could see what it was doing down below. And they had real nice connections. The connectors to connect pipes to vessels were remotely controlled. You could drop this tool down on the end of the crane and it would spin and unhook the pipe remotely, and they could change connections from way up in the cab, and it worked very well. And it was watertight, airtight when they got the connections made. That was real interesting work.
Now besides the ruthenium release that you talked about and the earlier green work, were there any other releases where you were able to get some practical experience on, on emergency releases?
They had a criticality, a nuclear reaction in a facility called Recouplex.
I remember that.
In which they were cleaning up contaminated material that had plutonium on it in a building called the Plutonium Finishing Plant. 234-5 building. And in this criticality, they had a tank with a solution in it, and somebody forgot to shut off a valve, and the wrong concentration ended up in the tank. And there was about 10 to the 17th fissions occurred in a burst, boiling out some of the water. They lost some of the moderator when they lost the water, so the next burst was smaller, and there was a series of smaller and smaller criticalities that occurred over time as this went on. The drain hose was improperly connected, you know, somebody had goofed. There were 3 people exposed. The highest was about 120 rem, including neutrons. And their blood count went down and some things like that, but they all survived very well after that. What I did...
The neutron dose was, did you get that from your quick sort method, or did you take blood, your whole body count? How did you determine
I'm not sure how they
dose?
got it. They probably they had neutron monitors, criticality monitors all around the building. And the people were wearing neutron badges. So they got most of the dosimetry off the badges.
Were there foils in the badges? Actually fission foils? Because I remember there was an elegant badge.
To measure different neutron energies.
I remember an 8-filter film badge when I was out there.
Quite
the most complicated thing I ever saw.
There were several foils and things in there, but not 8 that I remember. But anyway, it was interesting. We had stack monitor, and we were changing the stack monitor. We were worried about the environment. And we measured how much short-life cesium and rubidium, some other things that had gone out. And I calculated the dose at the plant boundary. The plume, we plotted the plume. When it finally crossed the site boundary, the dose rate, totally integrated dose rate, was something like 1 millirem or whatever. It was, you know, really innocuous. But the interesting thing I did, and I found out the travel time between the last HEPA filter in the system and the stack filter. And working backwards from the concentrations of the noble gas daughters that we collected on the filter, I calculated how many noble gases, how much each of the noble gases had been released, and had that much time to decay after this filter and deposit on the stack filter. And I worked backwards, and I ended up calculating how many fissions had occurred. And my calculation agreed within a factor of 2 with the chemist calculated from the contents of the tank that were left and about what they knew had been in there. So it was kind of fun. Had a lot of nice, fun things to do like that.
Now, did any alphas get out at all?
No. Now, all that stuff was collected by the HEPA filters. You know, they're 99.99% efficient. And fortunately, you know, they were all sealed tight. There weren't any leaks. And They did on occasion from the other parts of the building where they were doing the real processing of the plutonium. They would occasionally get small amounts of alpha on their air filters, but nothing to write home about. You know, it wasn't that.
Now, your whole body counting system was in full use back then, and so you were able to whole body.
By '63, I would say they had a whole body counting system. Yes, and
was that Resch design? Bill Resch's design?
Bill Resch designed it. He was in charge of the accelerator group that studied all that kind of stuff, and radiological physics, I guess it was called. He and Dick McCall worked together, and they stacked up sacks. I'm trying to remember whether it was sugar or gypsum or something like that to mock up a shield, and then they put a reclining chair, like a lawn chair, in the center, and a guy held the crystal against himself, and they kind of played with whole body counting. Then they built the iron room downtown in Richland, a big room where you had lots of space for counters, and we used it for counting thyroids. Also, some of us, I was telling you, we drank milk, and
with iodine in it, iodine 131.
Iodine 31, and there was iodine 31 in the milk in the stores, and some of us had our children go in there and get their thyroids counted for iodine 31 in the milk, and it got some interesting data. But no, the worst iodine contamination we got from fallout actually occurred up in Coeur d'Alene.
How's that?
May 26, 1953.
Yeah.
They had a bomb test that went straight north through California, whipped around through the Yakima area, the pine forest, and deposited rainwater with contamination in it in puddles in Richland. But the main part of the cloud went up to Spokane and the Coeur d'Alene area, and the highest milk, I think, was like 1,000 picocuries per liter up there. But
how far away was that, Joe, from the release point?
Coeur d'Alene from Richland would probably be 150 miles.
That's amazing. Because now, how did that jibe with the Gifford meteorology and atomic energy predictions?
Well, I don't know if anybody tried. But you know, they had a fellow named Bill Davis who worked at the Fallout branch down in Las Vegas. He was super predictor meteorologist, and he was a chemical engineer like I was trained. And here he was doing all this meteorological work. He came to Hanford later, and when we had the Chernobyl incident, he looked at the weather data from there, and he said there are 3 layers of wind, different directions, different speeds. There will be 3 plumes that reach the west coast of the United States. And one plume come in, the milk went up 100 picocuries per liter or something. EPA said later, oh, the concentration is going down, it's gone. In a little while, in comes the second plume, and the third plume, and he had it picked exactly. He had a time.
That's incredible.
It was super. And after Chernobyl, we had a group in Washington, D.C. who were not allowed to identify at the time, who was very interested in the dose that certain people might have got in Europe, probably somebody that they had employed over there. And they said, can you use your food model and emit data and tell us what doses might be to people over there, drinking milk, eating vegetables, standing on contaminated ground, all this stuff. So we used my simple food model. We made, the meteorologists made a grid, 170 places like this across Europe, all the way down to the Mediterranean. We got the met data, the wind data, the fallout data, the air measurements that we could, and rainfall data, and we calculated the doses to people. I divided Russia up in all the different little countries, you know, USSR. And I went to an almanac to figure out how many people were there, and I tried to lay out how many people in each area, and we played with the population data. And we ended up very quickly getting an estimate for the total man-rems for the area that we covered I can't remember the exact number, but it was within a factor of 2 of what DOE came up with. Their big committee that studied Chernobyl and radiation doses. Bill Baer was sort of in charge of that, and Marv Goldman, and Robert Schenker from University from Chicago area. He did a lot of the whole body counting data. They spent lots of time and money, and they got a dose, a collective dose that was about twice what we calculated. But it turns out they didn't like the Russian source term that we used. They tripled the cesium before they did their calculations. And so their dose was twice, but
was there any
the source term was 3 times as high, so we were within 50%.
Yeah. Was there any benchmarking of this data to try to see how realistic it really was? Well, versus people on the ground?
There were measurements on the ground, and there were measurements of deposition that were published. A lot of papers were published from people around the world.
IAEA put out a big map of showing it. Now, I thought that map
concentrations correlated fairly well, except
that's what I wanted to ask.
Okay, the problem was rainfall. They give you the rainfall total for the day. They didn't tell you what time of day. They didn't tell you it was a short, intense storm or light all day long. And if the cloud passed before the rain, you get different deposition than if it passed during the rain or after the rain. And that was the bug that fouled up some of our calculations. But overall, when all that's smeared out, over the whole area, again, law of compensating errors, the overall answer was pretty close to the correct one.
Well, I was so impressed with the data. I remember with some of the early commercial nuclear power plants, we were trying to figure out what the predicted dose would be from the emissions from the commercial nuclear power plants. And going back and finding out where the models came from, I kept seeing your name all the time. Again and again and again.
I'll tell you what happened. About 1980s, a fellow by the name of Dave Baker, who was a real good computer programmer. I know nothing about computers. I did mathematics, and other people did the computer work. But he took a food model, he took some of the air submersion distribution models that were developed at Hanford, put them together, and for the DOE, he calculated population doses, maximum individual doses, around each of the operating nuclear power plants in the United States for a series of years. That was his assignment. He would get the effluent data, and then he would make these calculations and publish them. So that's probably where he saw the data, and part of the code he used, the mathematics at least, was developed by me. Dave and I are the ones that put together what was called the critter model.
Yes,
one of the first comprehensive aquatic biota dose models. And there again, there's what's the half-life in a bird or fish? We had to use human data for half-life. I had to use the models I had developed for the 4 age groups of people for 50-year dose commitments for infants, child, teen, adult. I developed all that stuff with tedious handwork over the years. We used that kind of data for animals, but changing the organ size. A whole body dose to a fish. Well, what does a fish represent in terms of a sphere? It's like ICRP2 did with our organs. They made spheres out of them. And for biological half-lives, we had to use human data a lot, or kids' data, whatever. And of course, then we had to calculate in rads instead of in REM, because we were told, oh no, REM is only for humans, so you got to use rads. Well, a lot of the effective energies that we used, especially like for alpha, had weighting factors of 10 or 20 in them, and we had to unfold the effective energies to get that back out before we could use it for the biota. So there was a little bit more handwork to take care of that. I gave a paper on that at the mid-year symposium health physics in Coeur d'Alene. And that was published in the proceedings.
I remember that. Now, for some of our younger viewers, could you tell us about the famous Soldat theory of compensating errors for all environmental data? I love that.
Well, I told you what happened at PRTR.
Yeah.
When I waved the GM over to charcoal, and I guess the milk would be less than 20, and it turned out to be 18.
Yeah.
But the wind went a different way, and I forgot about the short-lived iodines and the charcoal and all. We had a sample and at a facility called Hot Semiworks, which was studying the conversion of strontium and cesium collected from the waste tanks to a form that could be encapsulated and used as sources. It was shipped to Oak Ridge after they got done with it, and Oak Ridge played with it a little while too. And one day they had a release of strontium-90 from the stack. We had an air filter, stack filter sample, or it was the same size as the end window on a CP. I changed the sample, read it with a CP, and I went through mental calculations to convert it to counts per minute because I had a conversion for counts per minute for strontium-90. And I guessed how many microcuries were on that filter. I knew what the stack flow was, the sample flow, and the time. So about 50 microcuries went out. And they sent it to the lab. In the meantime, I talked to Wyatt Selker, the guy I mentioned before. He had measured strontium-90 in soil around the project, mostly from fallout. And he said, well, 50 microcuries, the peak on the ground will be at the fence line of that facility, and it'll be less than what's there from fallout. You might not ever find it. Might not ever find it. When the lab came back with my estimate of 50 microcuries, turned out to be 49 microcuries.
That's amazing.
Yeah, and there was a third one. I'm trying to remember what it was where I made a guess like that, and I came out with, they asked me to sample krypton 85 from the reprocessing stacks. They wanted a beta emitter, which would not contaminate the piping at the plutonium recycle test reactor with our tritium monitors. It was a heavy water moderated reactor, which generated tritium when it was running. And it's, can you get a sample of krypton 85? Well, try and do that today. You have 2 years of paperwork for EPA and the state and everybody, and then in the end you probably couldn't do it. But
well, what did you do?
Well, we had little cards that said we could carry radiation meters, radioactive samples. So I went out by myself, suited up, went out to the sample shack, and they had a facility that was called acid recovery, so they could recycle the nitric acid, which I decided was a better place than the main stack to try and get pure krypton. And I put together a sample train of filters and caustic scrubbers and another blower. I blew the exhaust into a 40-liter plastic bag, half full. I sealed it up and wrapped it around a CP, and I said, that's an infinite volume. And I measured the dose, and I said, well, if that was an infinite volume, there's krypton with the energies it's got and so on. That's so many microcuries per cc in that bag, and that ought to be enough for them. So I threw it in the trunk of the car and drove it back 20 miles, 15 miles to 300 in the lab. And they measured it, and their measurement was within 10% of what I had. I was kind of, nobody's going to believe this. So when I wrote my monthly report, I said, well, I was within 20%. But, you know, we used to do all kinds of fun things like that. And I've always maintained, and still do today, you get a couple of really experienced HPs and a pocket calculator in the back of an envelope in an emergency, and they could tell you real quick, like, whether you've got a real serious problem, whether you need to evacuate a school somewhere, or what. And then you can wait 30 minutes for the computer printout to tell you what the second decimal place is. But all you need is an order of magnitude at first in an emergency.
You know, that's a wonderful rule, an important rule of thumb, too. Well, Joe, we're beginning to run out of time here, so we should wrap this up. But how about a bit of wisdom from you on the young people coming into the health physics field, and especially the environment is very important today, into the field of where they're interested in measuring radiation in the environment. What do you see happening here? What are your words of wisdom for the young health physicists just entering the field now?
Good question. I'm not the wisest man in the world. Like I said, I've had a lot of experience. What I see going on a lot, especially when I go to these health physics meetings, is people rediscovering the wheel. and or maybe deciding that the wheel, the gear has 16 teeth instead of 14 or something, which is not earth-shaking. And I would recommend that everybody do a literature search and find out what has been done before in the area that they want. In my later years, I was a sort of a mentor out there, and the young people would come to me and I've got a problem with sediments in the river and contamination. Have you ever done anything? And I'd say, okay, here's a half a file drawer, help yourself. And you need to find somebody, you know, if you can't find the literature, at least find an experienced HP that you can talk to who might at least know where you can go to get some references or some data. And if you don't know one, you could find them in a handbook. There's got to be one in your area. We're all over the country now.
Well, Joe, thank you so much. I've enjoyed this thoroughly and learned a huge amount from listening to you. And I look forward to putting this tape in the archives and being able to play it, especially for people in the environmental field, because you've contributed so much. And so thank you so much.
Well, I enjoyed talking, as you probably realize.
Thank you very much.